sky. And there are departments in research institutes which are basically focused on looking and studying fractures in failed machine parts. Because if you look at a fracture, you can tell a lot about how it happened. So, for example, if an aeroplane crashes, they want to know why it crashes, why something has broken. And by looking at the fracture, you can actually understand what has happened. So here is a fracture in a sandstone just close to Aachen. And you are now looking on the fracture itself. So the other half has been taken away by erosion. And what you see is that this fracture is more or less elliptical. And it has these circular bands on it. And if you look carefully, the circular bands have different colors. This is more shiny than that one. And that is because the fracture surface changes orientation. Okay? So the fracture is circular, and there are these conically shaped, differently oriented parts to it. And then what you also see is when you look here, it is very smooth. But here on the side, it is much more rippled. There are little steps in it. And the reason why these things form is because this fracture has started in the middle and has grown in all directions. Here is another very beautiful example from Israel. I got this from a colleague who works in the Israeli Geological Survey. Here is a fossil, a little hole in the rock. And around this fossil you have these circular structures. And this fossil was actually the place where the fracture initiated. And from there on it has grown in all directions. And in this thing you can see a little fossil in the middle, and then the fracture has grown in horizontal direction because it was growing inside the layer, between the layer boundaries. So these are the nucleation points, and these are basically these circular features mark the times of where the tip of the fracture was over time. And in this case, you can even see 3 of these nucleation points, circular marks between the boundaries of a layer. So the fracture grows, but it cannot cross the boundaries between layers. Okay, so this is very interesting. Now let's look at a very much bigger fracture. This is in granite in the Pergel Massif in the Alps. There are some trees here for scale, so this could be about 50 meters. And this is a big fracture, and you can see that here the fracture is one plane, but here there are steps. There are 3 steps. So the fracture itself has a very complicated 3-dimensional geometry. At the bottom, on the left side here, the fracture is continuous, and then it kind of splits. Okay? And one part of the fracture goes away in this direction, and the other, it goes away in a slightly different direction, and you have these 2 kind of offsets in the fracture. This fracture has grown from this side to that side. So summarizing, joints are formed in extension. They have a lot of very interesting features on the surface. You have these concentric marks which tell you where the fracture was over time, and then you can have these steps which are called fringes, and there are some names here like conchoid structure and plumo structures which maybe you want to remember or learn about. So by looking at fractures, at fracture surfaces, we can tell a lot about how these fractures have opened, and so forth and so forth. But before we can go on and understand more about fractures, we have to now do a little bit of mechanics again. What I've explained to you until now is that if you make a tension on a rock sample, it will split perpendicular to sigma 3. Okay? And that's very important. Joints are not like the faults here. Joints grow perpendicular to sigma 3. why does a fracture grow like it does? For that, we have to understand a little bit of the mechanics of how a fracture propagates. Okay? We have seen now that the fracture starts somewhere and then it kind of grows into the material. What is very important here is that fractures, the tips of fractures, are places where the stress in a rock is concentrated, very, very much higher than it is further away in the material. And to explain that, I made a few little calculations for you. And I will start not with a fracture, but with a cylindrical hole. Okay? So here is the material, and far away from this hole, I have drawn a stress which is vertical, and the horizontal stress in this case is almost zero. Okay? So in the Moore diagram, my stress is something like this. One stress is zero, and the other is vertical. There is no fracture here, so I've drawn the Moore circle so that it doesn't actually touch the line. But this is now the stress. And remember, I explained to you that a free surface must be a principal stress. So what this hole does to the stress field is that it, first of all, turns the principal stress everywhere so that the one is parallel and the other is perpendicular to the hole. And the other, what it does, is that it takes up some of the load which is now not carried by this hole. If we would have a piece of rock completely homogeneous under stress, it would be in equilibrium, right? So, in this rock, let me just give you an example. Stresses would be everywhere like this. A very small sigma 3 and a larger sigma 1. These are the directions in the stress field. So if we imagine this little circular area here, this rock is actually pushing back, right? It is supporting the rock around it. Now if we take this away, the hole would want to collapse, but it doesn't because the rock is strong enough and the stress is taken up by the rock around it. So the stresses around the hole are a little bit higher, and close to the hole it is about 3 times as high as far away. So 2 things to remember. Around the hole, stresses are about 3 times higher, and the principal stresses are kind of around the hole as in a ring. And in the same picture now, I have calculated for you the magnitude of the stress. Okay, so far field is this blue color. It's about 8 times 10 to the 7, and far away it is now green. It is about 23, about 3 times as high. Okay, in this particular place. Now I've repeated the same experiment, exactly the same stress, no plasticity, no fracturing, but now I made the hole not circular, but elliptic. So there is a more sharp corner. And if you do that, you get something very similar, but the stresses here become higher. Okay, so you go up here, and if I make the ellipse even bigger, remember this is not a deformation that I'm showing you. I calculate every time a model with a different hole in it. Then you are already in the red colors here. So if you make this ellipse flatter and flatter, the stresses at the tip, at the sharp tip of the ellipse, go up and up and up. And if you want to do this until the ellipse is completely flat, then what you will find that the stresses at the tip of the ellipse become infinite. A very, very flat ellipse has extremely high stresses at its tip. And how high these stresses are is a rather complicated issue. I don't want you to learn these formulas at all. Okay, I'm just showing you that the stress components, okay, here, depend on this R here, which is below the line in the formula. And R is the distance to the tip of the crack. So if you have an infinitely sharp crack tip, and you go closer and closer to the tip of the crack, the stress becomes higher and higher and higher. And because it is a 1 over R function, the stress will become infinite at the tip of the crack. So an infinitely sharp crack at the tip has infinitely high stresses. Hey, now this is something to think about. Because how can you have infinitely high stresses in a rock material? Of course, any rock has a strength. And if the stresses will become high enough, the strength will be exceeded and the rock will fail. So clearly in theory, you can derive the equations saying that the stresses are infinite at the tip of the crack, but that is in practice not possible. What happens in practice is, these are some very beautiful photoelastic simulations of the stresses at the tip of the crack. And this is an atomic model of the tip of a crack. So we are now looking at Angstrom scale at the crystal structure. And what you see is that the crack at one point is not sharp anymore. If you go down to the Angstrom scale, the crack is rounded. And the reason is that the moment it becomes too sharp, some of the bonds in the crystal will break. And the fracture will propagate. So a fracture tip, if you look at the atomic scale, is never completely sharp. And this is the explanation to tell you, or to explain to you, why the stresses cannot be infinitely high. So, a sharp crack tip has very high stresses. And a very beautiful illustration of that is by cutting glass. I put a picture here of a glass cutter. You all know that glass can be very strong, but if you want to break glass, it's very easy to make a tiny fracture, and then you can snap it like this. And that is because this fracture concentrates the stress, and it will guide the fracture. In theory, again, there are 3 different kinds of fractures. There is the mode 1 fracture. This is what we have talked about, which opens like this. There is the mode 2 fracture, which works like this. And this is the mode 3 fracture, which is a kind of a scissoring fracture. And these fractures, these mode 1 fractures, they always propagate perpendicular to sigma 3. So just one more picture of how these fracture surfaces look like. The fracture started here. There has been a very, very high stress at the tip of it, high enough to break the rock, and the fracture propagates. And what has happened here is that during the propagation of the fracture, okay, so let's say that my hand is the fracture, and sigma 3 is like this, okay? During the propagation, the fracture has encountered a stress field which is not exactly parallel to it anymore. So the stress has actually rotated in front of the fracture, and then the fracture wants to do this. It wants to turn into perpendicular to sigma 3, and to do that, the fracture does this, and it breaks up into these fins. This is what has happened to this fracture. Going back to the scale of the crystals, not to the scale of the atom,